Look, I'm going to level with you right from the start. Something happened in October that nobody's talking about enough. Something that has some of the world's best astronomers scratching their heads and asking questions they never thought they'd need to ask. And I'm not exaggerating when I say this could be one of the most important moments in astronomy we've had in decades. This isn't about another comet passing by. We see those all the time. This is about a visitor that traveled billions of years through the darkness between stars, a visitor that arrived and did something completely unexpected, something that breaks almost everything we thought we knew about how these interstellar objects should behave. Let me tell you what happened, because once you understand the details, once you see the data, you're going to understand why scientists are genuinely freaked out about this thing. And by genuinely freaked out, I mean concerned in the way that makes you question your fundamental assumptions about the universe. On October 29th, 2025, something called Threeey Atlas reached its closest point to our sun. This is an object that's been traveling through the vacuum of space for somewhere between 7 and 12 billion years. That's right, billion with a B. This thing was wandering through the galaxy before our solar system even existed, before Earth, before there were any planets at all, and then it shows up at our doorstep, and when it gets close to our sun, something extraordinary happens. The brightness doesn't just increase like we'd expect, it doesn't gradually get brighter as the sun heats it up. The brightness surges at double the rate. It literally doubles its rate of increase right at perihelion. That's the closest point to the sun, and that's when all hell breaks loose. Two astronomers watching this in real time, Chi-Chang Zhang from Lel Observatory and Carl Batams from the U.S. Naval Research Laboratory, they literally had no explanation for what they were looking at. Think about that. These are trained professionals who study comets for a living. They understand how these objects behave, and they watch this thing do something that their models completely failed to predict. The surprise on their faces must have been something else. Here's where it gets really interesting. The light coming from this comet, when scientists analyzed it, became bluer than the sun itself. When light shifts blue, it tells us specific molecules are present, in this case carbon molecules, C2 molecules, and imidazine compounds with the chemical signature NH2. These are the fingerprints of ice actively turning into gas. Sublimation, that's what it's called when ice just vaporizes directly into space without becoming liquid first. It's a real phenomenon. We see it on Earth with dry ice, but the rate at which it was happening with Threeey Atlas, that was insane. In just 14 days leading up to the closest approach, this thing was ejecting approximately 5.7 times 10 to the 28th power water molecules per second. Now, I know that number means absolutely nothing to you, so let me put it this way. It was losing water 40 times faster than it had been losing water just 1 month earlier. 40 times. One astronomer described it as a fire hose on full blast. Imagine turning on a faucet and having the water pressure suddenly multiply by 40 in just a few weeks. That's what we're talking about here. Now, you might think, okay, that's actually normal for a comet. Comets heat up, ice turns to gas, they get brighter. Basic physics, high school textbook stuff, except here's the problem. Threeey Atlas isn't following the basic physics textbook. The rate of change is wrong, the timing is completely wrong, and the way it's behaving doesn't match anything we've observed in our own solar system with the comets we've been studying for centuries. Space telescopes caught all of this, SOHO Stereo A and the brand new GOES-19 satellite. These instruments have special coronagraphs that let them observe objects really close to the sun without burning out their cameras. When these telescopes took pictures of Threeey Atlas during this period, they saw something that looked like a faint, stretched out glow. But here's the thing that made everyone go silent. No dust tail, none, zero, and nothing. If you know anything about comets, you know they have tails. That's literally the most iconic thing about them. That beautiful sweeping tail that looks like a brushstroke across the sky. The Hubble Space Telescope images of Hale-Bopp, right? That gorgeous tail stretching across the night. That's what comets do. They shed material as they get closer to the sun, and the solar wind blows all that material out behind them, creating the tail. But Threeey Atlas, it had no visible dust tail, just this elongated glow without any of the characteristic dust trail. Scientists have some theories about why. One hypothesis goes like this. Early on, as Threeey Atlas approached the sun from far away, carbon dioxide gas was escaping from it. This CO2 was creating a protective layer that actually cooled the surface. It was like a shield, and while that shield was there, the water underneath couldn't vaporize because it wasn't getting hit with direct sunlight. But then something changed. That protective layer of CO2 depleted. It ran out, and when it did, boom, the water ice that had been protected suddenly got exposed to direct solar radiation, Massive overexposure, sudden vaporization, explosive increase in brightness and activity. It's plausible. It fits what we know about physics. It explains why the surge happened so suddenly, but here's the thing that keeps nagging at some researchers. Not all, but some. What if the explanation is something else entirely? What if the nucleus of this object, the solid core inside, is fundamentally different from anything we've encountered before? Remember, this thing didn't form in our solar system. It didn't form around our sun. It formed around a completely different star in a completely different environment with different chemical conditions. The periodic table was the same everywhere. The laws of physics don't change. But the way materials formed, the way elements combined, the ratios of different compounds, the internal structure of the object, that could be completely foreign to us. And then the James Webb Space Telescope got involved. This machine is the most advanced telescope humanity has ever built. It can see into infrared wavelengths that give us information about composition that visible light never could. When Webb analyzed Threeey Atlas back in August, before it got closest to the sun, its near-infrared spectrograph found something profound. This object has been transformed, and I don't mean transformed like it's aged a little bit. I mean fundamentally, chemically, structurally transformed by billions of years of cosmic ray bombardment. Let me explain what that means, because this is actually the creepy part of the story. In our solar system, we're protected. The sun creates this bubble called the heliosphere. It's like a magnetic shield created by the solar wind streaming out from our star. This bubble protects us from most galactic cosmic rays. These are these incredibly high-energy particles that come from supernovae and other violent events across the galaxy. We're shielded, we're safe inside our little bubble. But in interstellar space, there's no bubble, there's no protection. Objects drifting between the stars are exposed to the full intensity of cosmic ray bombardment. Full intensity for millions or billions of years, just getting hit repeatedly by these particles that tear through material and change the chemical structure at the molecular level. A researcher named Roma Mahiolo and his team from the Royal Belgian Institute for Space Astronomy studied this. They created computer models to understand what happens to ice and rock when it's exposed to cosmic rays for extended periods. The simulation showed that after approximately 1 billion years of radiation, the transformation is complete. The outer layers become something different. Carbon monoxide turns into carbon dioxide. The crystalline structure of the ice changes completely. Chemical bonds break and reform in new configurations. The result, a crust extending roughly 50 to 65 feet deep into the comet's interior. A shell of radiation-processed material that no longer represents the original composition from wherever this thing originally formed. And here's what's unsettling about that. We don't actually know how thick this crust really is. We don't know if solar heating will just erode it away and reveal pristine material from the original stellar system underneath, or if this entire object has been transformed all the way through to the core. We just don't know. Maggiolo made a really important point, though. He said that scientists need to take these aging processes into account when analyzing Threeey Atlas. You can't just assume you're looking at a fresh sample from another star system that's going to tell you all about what that system is like, because you're not. You're looking at something that's been modified, heavily modified, by the harsh environment of deep space for billions of years. But then he said something hopeful. He said Threeey Atlas remains incredibly interesting despite this complication, because if we can understand how this radiation crust formed, if we can compare observations from before perihelion with observations after perihelion, when solar erosion might have exposed deeper layers, we might still be able to glimpse the original composition. That's what astronomers are waiting for right now. That's what makes the next few weeks so critical. The comet has passed perihelion. It's moving away from the sun, and right now, in November and December of 2025, it's becoming visible again from Earth as it continues its trajectory out of our solar system. This is our window. This is when we might see if the solar heating stripped away enough of that radiation crust to reveal what's underneath. Now, here's something that most people don't know about. There's a professor at Forschungszentrum Jülich in Germany named Suzanne Falsner, and she's proposed something radical about interstellar objects like Threeey Atlas. She suggests these objects might not just be cosmic debris floating around, they might actually be the seeds of planets. Her computer model shows something fascinating. Young stars surrounded by their planet-forming disks of gas and dust could capture millions of interstellar objects as as they drift through the galaxy. And once captured, these objects, which are already hundreds of meters in size, it could serve as the nucleus around which entire planets grow. Now, why does this matter? Because there's actually a huge problem in planetary science that nobody really talks about much. We know that planets form through accretion. Small particles stick together to form larger objects, which stick together to form even larger objects, and eventually you've got a planet. But there's a gap in our understanding. Computer simulations show that once objects reach about a meter in size, the chaotic environment of a protoplanetary disk should cause them to collide and shatter rather than stick together and grow. So how do you get from meter-sized rocks to planet-sized worlds? How does that bridge get crossed? Falsner's answer is simple and elegant. You don't start from meter-sized rocks. You start with interstellar objects that are already large enough to gravitationally attract material and begin the planet-building process all on their own. Interstellar space delivers ready-made seeds for the next generation of planets. It's like the universe has this cosmic delivery system that sends out raw material to seed new planetary systems. And her models suggest this process works especially well around massive stars, stars larger than our sun, which would explain something astronomers have been puzzled by for years. Why are gas giant planets like Jupiter more commonly found around larger stars, even though the planet-forming disks around those stars only last about 2 million years? That's a really short time, too short a time for traditional planet formation theories to work if you're starting from scratch with dust and gas. But if you've already got these massive interstellar objects with seeds arriving as building blocks, then suddenly 2 million years makes sense. Suddenly the timeline works. So when you look at Threeey Atlas, you're not just looking at a comet, you're potentially looking at the kind of object that could have become a planet if it had been captured by a young star billions of years ago. You're looking at a building block of worlds that never got built, a missed opportunity, a planetary embryo that never developed into a full planet, and that changes the entire context of what we're observing here. But let's talk about what's happening right now, because the most intriguing aspect of this whole story isn't just what we've discovered, it's what we still don't know. The trajectory of Threeey Atlas is unusual. This thing is traveling at over 130,000 miles per hour relative to our solar system. That's fast, but more importantly, it's traveling in what observers have described as an unusually flat and straight path. Think about that for a second. Most objects that formed in our solar system have been influenced by planetary gravity for billions of years. Their trajectories are curved and chaotic. They bounce around the solar system. They get pulled this way and that way by gravitational interactions. But Threeey Atlas, straight line, flat trajectory at an angle to the ecliptic plane that just screams, I came from somewhere else and I'm just passing through. Some estimates suggest this object could be between 7 and 12 billion years old. That would make it approximately 3 billion years older than our entire solar system. 3 billion years. Think about that. This object existed before our sun even ignited nuclear fusion, before Earth formed, before any of the planets we know came into being. It has been traveling through the galaxy since a time when the Milky Way looked completely different than it does today. The structure was different, the stellar populations were different, the radiation environment was different. What has this object seen? What stellar environments has it passed through? What planetary systems did it drift by in the darkness? Never quite close enough to be captured, but close enough to feel their gravity, to be influenced by their radiation, to pass through their stellar winds. We know it came from somewhere in the galactic frontier, possibly from the outer regions of the early Milky Way, but we don't know where it actually formed. We don't know what star it orbited. We don't know what happened to that star. Did it go supernova? Did it evolve into a red giant? Did it collapse into a white dwarf? We don't know if Threeey Atlas was ejected from a young planetary system by the gravitational interactions of forming gas giants, or if it simply condensed in the space between stars and has been wandering ever since. What we do know is that right now, at this very moment, Threeey Atlas is moving away from our sun, heading back out into the darkness, and we have a limited window, really limited, to gather as much data as possible before it fades from view forever. Once it leaves our solar system, we'll never see it again. This is a one-time opportunity. This is it. We won't get another chance. And that brings us back to something important. Professor Avi Loeb, who was the former chair of Harvard's astronomy department, has formally requested that NASA release all scientific data on Threeey Atlas to the public. All of it. He wants it transparent. He wants independent researchers to have access to everything. Why would he do that? What does he think might be in that data that NASA hasn't shared yet in their press releases and preliminary papers? Loeb has a history with this kind of thing. spring, he was one of the leading voices calling for serious scientific investigation of something called Oumuamua, which was the first confirmed interstellar visitor we detected back in 2017. That object had an elongated shape that seemed weird. It had an unexpected acceleration as it left the solar system that couldn't be explained by outgassing alone, and it lacked visible comet activity. All of these things were anomalies, and Loeb argued then and maintains now that we should not dismiss unusual possibilities when we're confronted with unusual data. He argued that we should investigate those anomalies rigorously rather than rushing to find comfortable explanations. Now, with Threeey Atlas, Loeb is making the same case. His argument is straightforward. This is an object of extraordinary scientific importance. It's only the third confirmed interstellar visitor we've ever detected in human history. The data collected by NASA's instruments, by the Swift telescope, by SOHO, Stereo, and GOES, 19 represents humanity's best chance to understand what interstellar objects are really like. And that data shouldn't be locked away, it shouldn't be siloed in government agencies, it should be available for independent analysis by researchers around the world, different perspectives, different expertise, different ways of looking at the same information might reveal patterns that a single agency or research group might miss. But here's the thing, there's an unspoken question underneath Loeb's request. What exactly is in that data? What has NASA observed that hasn't been publicly discussed? Are there measurements, spectra, behavioral patterns that don't fit easily into press releases? Are there anomalies that raise more questions than answers? The scientific community is divided on how to interpret Threeey Atlas. Some researchers are comfortable with the explanation that it's simply a comet with an unusual composition that's been modified by cosmic radiation over billions of years. They point to the carbon dioxide, the water vapor, the molecular signatures. That's what they say is a comet, just a weird one. A comet we've never seen before because we've never studied an interstellar comet this closely. These researchers sleep well at night. But others are less certain. They're quieter about it, but they're asking questions in research papers and conference presentations. They point to the anomalies, the explosive brightening that doesn't match the models, the missing dust tail, the perfectly flat, straight trajectory, the possibility that the internal structure is fundamentally different from anything in our cosmic neighborhood. And they ask quietly what else could explain these observations, what else? And here's the thing, nobody wants to be the scientist who jumps to conclusions without evidence. Nobody wants to be labeled as a conspiracy theorist or a science fiction writer in a lab coat. So the questions hang in the air like the comet's own glowing coma, unspoken, uncomfortable, but they're there. What if Threeey Atlas isn't entirely natural? What if there's something about its composition, its structure, its behavior that suggests it's more than just a ball of ice and rock that's been drifting through space for billions of years? Now, before you dismiss that as science fiction, let me be clear about something. I'm not saying that's the case. I'm saying it's a question worth asking, and here's why. We have no framework for answering that question. Our entire scientific understanding of comets, asteroids, and interstellar objects is based on natural formation processes. We look at spectra, we see carbon dioxide and water, and we think comet, we see an elongated shape, and we think fragment from a planetary collision or tidal disruption. We see a trajectory, and we calculate gravitational interactions with other stellar systems. It's all based on natural processes. But what if the signatures we're trained to interpret have multiple possible explanations? What if some of the things we're seeing could be consistent with both natural and artificial origins? How would we even know the difference? How would we test for it? Now, I'm not saying that Threeey Atlas is artificial. I'm saying we should be thorough enough to consider all possibilities and then rule them out with evidence rather than just assuming we already know the answer because that's the comfortable answer. This is not about declaring Threeey Atlas is anything other than what it appears to be. This is about acknowledging something important. Our sample size for interstellar objects is exactly 3. Oumuamua, Borisov, and now Threeey Atlas. 3 objects out of potentially billions or trillions of objects drifting through our galaxy. 3, and we're drawing conclusions about an entire class of cosmic phenomena based on 3 examples. That's not science, that's preliminary observation at best, and each of those 3 has surprised us. Oumuamua accelerated in a way that couldn't be explained by outgassing alone. Borisov was relatively normal, but came from a different stellar environment with different chemical signatures than we expected. And now Threeey Atlas is brightening explosively, losing water at unprecedented rates, and challenging our models of how irradiated comets should behave. Maybe all 3 are just natural objects with unusual properties. Maybe the universe is far more diverse than we've given it credit for, and every interstellar visitor will teach us something new about the variety of environments and formation processes across the galaxy. That's probably the right answer. That's probably what's happening. It's the simplest explanation, and it's probably correct. But the explosiveness of Threeey Atlas's brightening, the timing of it, the way it happened right at perihelion, that precision, it keeps nagging at some researchers, because there's a difference between unusual but explainable and unusual in a way that suggests something we haven't considered. There's a difference. Let's talk about what happens next, because the story of Threeey Atlas is far from over. As the comet moves away from the sun, it will remain observable through November and December. Astronomers around the world are pointing their telescopes at it. They're collecting spectroscopic data, measuring its brightness, tracking any changes in its activity level. The question everyone wants answered is simple. Will the activity decrease now that it's moving away from solar heating, or will something else happen? Chi-Chang Zhang and Carl Batam specifically noted in their observations that the post-perihelion evolution of this comet could be just as unusual as the pre-perihelion outburst that preceded it. What did they mean by that? What are they expecting? Or perhaps more accurately, what are they concerned might happen? One possibility is that the comet will simply fade as expected. The solar heating decreases, the sublimation slows down, the brightness drops, and Threeey Atlas becomes a dim speck gradually disappearing into the darkness. That would be the normal scenario. That's what the textbooks predict. That's what we'd expect. Another possibility is that the activity continues or even increases if there's something inside the nucleus that's now been exposed by the erosion of the outer layers, some volatile material we don't know about. It could continue outgassing even as the comet moves away from the sun. That would tell us the internal composition is radically different from the surface. That would raise questions, big questions, but there's a third possibility that no one wants to say out loud. What if the behavior changes in a way that can't be explained by solar heating at all? What if there's a pattern to the activity that suggests internal processes rather than external heating? What would that mean? What would we conclude from that? Here's something most people don't realize. The two Mars rovers, Curiosity and Perseverance, actually had a unique opportunity to observe Threeey Atlas from their vantage point on the Martian surface. Different angle of view, different perspective. Their observations could reveal details invisible from Earth, different triangulation, but the data from those observations hasn't been fully released yet. What did they see? What did those rovers capture that might tell us something new? When Threeey Atlas came close enough to the sun, the solar wind, that stream of charged particles flowing out from our star, would have interacted directly with its coma, the cloud of gas and dust surrounding the nucleus. That interaction creates effects. We're talking about plasma instabilities, magnetic field distortions, particle acceleration. These effects can tell us about the composition and structure of the comet in ways that simple spectroscopy cannot. It's like a different diagnostic tool, different information. NASA's STEREO mission, specifically designed to study the sun and its influence on the space environment, captured images showing Threeey Atlas interacting with the solar wind. Those images revealed structures in the coma, asymmetries in the gas distribution, patterns that suggest complex dynamics at play, but interpreting those patterns requires understanding not just comet physics, but plasma physics, magnetohydrodynamics, the chaotic environment near the sun. It's complicated. It requires expertise from different fields. This is why Loeb's call for data transparency matters so much. The more eyes on this data, the more perspectives brought to bear, the better chance we have of understanding what's really happening. Maybe one research group will notice something another group missed. Maybe an independent analysis will reveal a pattern that changes the entire interpretation. Science works best when it's open, when data is shared, when unusual observations are met with rigorous analysis rather than premature dismissal. And Threeey Atlas is unusual enough that it deserves that level of scrutiny. Now, let's address something that's been circulating in online discussions and amateur astronomy forums. Some people have noted that the timing of Threeey Atlas's outburst, coinciding almost exactly with perihelion, seems too precise, too coincidental. Natural processes are often messy, chaotic, with gradual changes rather than sudden transitions. But this brightness surge happened exactly when the comet reached its closest point to the sun. Why? The scientific explanation is threshold effect. As the comet heated up, it reached a critical temperature where the sublimation rate suddenly increased. The protective CO2 layer depleted at a specific point, and once it did, the water ice underneath was exposed all at once. leading to rapid brightening. That's plausible. That fits known physics. That works mathematically. But there's an alternative interpretation that some find compelling. What if the object was designed to activate at a specific distance from a star? What if the outburst wasn't caused by passive heating, but by some internal process triggered by proximity to our sun? Before you dismiss that as science fiction, consider this. We've already sent probes to other planets that activate at specific times or under specific conditions. We've built satellites that wake up when they detect solar radiation above certain levels. We've engineered spacecraft with threshold-triggered systems. The concept of a threshold-triggered system is not exotic. It's not science fiction. It's basic engineering. We do it all the time. The question isn't whether such a thing is possible. The question is whether there's any evidence that Threeey Atlas is anything other than a natural object, and the honest answer is we don't have enough data yet to rule anything out conclusively. We just don't. We're still gathering information. What makes Threeey Atlas particularly intriguing is its mass. Early estimates suggest this object has a mass of approximately 33 billion tons. That's enormous for a comet. Most comets we observe from our own solar system are much smaller. The nucleus of Halley's Comet, the famous one, the one that comes back every 76 years, it's estimated at around 22 billion tons, so Threeey Atlas is significantly more massive than one of the most famous comets in human history. Now, mass alone doesn't mean anything unusual. Larger objects exist throughout the solar system, but combined with the other anomalies, the high velocity, the explosive outgassing, the unusual trajectory, the missing dust tail, it adds another data point to a growing list of things that make this object stand out. And then there's the velocity. 130,000 miles per hour might not sound extraordinary in cosmic terms, but it represents a specific energy state. This object is moving fast enough to escape not just our solar system, but to travel between stellar systems over billions of years. It's been in transit for so long that the star it originated from might not even exist anymore. That star could have evolved off the main sequence, swelled into a red giant, shed its outer layers, and collapsed into a white dwarf. All while Threeey Atlas was wandering through the darkness, all of that happened and the comet kept going, kept traveling, kept surviving. Think about that journey, 7 to 12 billion years. If the age estimates are correct, this object has been traveling since before complex life existed on Earth. It passed through regions of space we can only theorize about. It survived encounters with who knows how many stellar systems, gravitational perturbations from massive objects, radiation from sources we can't even identify, and it emerged from all of that intact, still coherent, still recognizable as a discrete object rather than dispersed into a cloud of debris. That in itself is remarkable. The survival rate for objects traveling through interstellar space over billions of years should be relatively low. Collisions with other objects, gravitational disruptions, radiation damage that causes structural failure, all of these are threats to an object's integrity. Yet Threeey Atlas is here, apparently intact, apparently functioning in ways that suggest it's held together remarkably well despite its ancient origins. The irradiated crust that Webb detected might actually be part of the answer. That 50 to 65 foot thick layer of radiation processed material could be acting as protective armor, shielding the interior from further damage, maintaining structural integrity. It's a shell forged by billions of years of cosmic ray impacts. Harder and more resistant than the pristine ice underneath. In a sense, the journey itself made Threeey Atlas more durable. The thing that aged it also protected it. But here's where it gets interesting from an engineering perspective. If you were designing a probe to travel between stellar systems, hypothetically just as an intellectual exercise, if you were designing something to survive the harsh environment of interstellar space for billions of years, what would you do? What would your design look like? You'd need protection from radiation, absolutely. You can't have cosmic rays destroying your internal structure. You'd need structural integrity that could withstand micrometeor impacts. Space isn't empty, there's dust, there's particles, there's debris. You'd need a design that could handle extreme temperature variations. You'd probably want it to be mostly passive, not requiring active systems for the majority of the journey, only activating when it encountered specific conditions. Maybe when it approached a star, maybe when it detected certain radiation signatures. An irradiated crust would serve many of those functions. It would protect the interior. It would provide structural strength. It would be formed naturally by the environment, requiring no active maintenance. And if there was something underneath, something that needed to remain dormant until triggered by proximity to a star, that crust would keep it safe, protected, preserved, hidden. Now, I'm not saying that's what Threeey Atlas is. I want to be clear about that. I'm saying that if you look at the characteristics we've observed, the age, the mass, the protective crust, the threshold-triggered activity, the unusual trajectory, you're looking at properties that would also be consistent with a designed object meant to travel between stars. That doesn't prove anything. It doesn't make any claims. It just means we should be thorough in our analysis. It means we should look at all possibilities before deciding what we believe. This is why the scientific method exists. You don't start with conclusions, you gather data, you test hypotheses, you look for ways to distinguish between competing explanations. And right now we need more data, we need observation, we need analysis. The observations coming in over the next few weeks will be critical. If Threeey Atlas fades predictably, if its behavior matches refined models of irradiated comets influenced by solar heating, then we'll have a good natural explanation for everything we've seen. The anomalies will be explained as the result of unusual but understandable composition and environmental history. We can write the paper, publish the results, move on to the next mystery. Case closed. But if the behavior continues to deviate from predictions, if there are patterns in the activity that don't correlate with solar distance, if the spectroscopic data reveals compositions or structures that challenge our understanding of natural comet formation, then we'll need to expand our hypothesis space. We'll need to consider possibilities that currently seem unlikely, and that's uncomfortable for many scientists, because once you start entertaining hypotheses that fall outside the conventional framework, you open yourself up to criticism, you open yourself up to accusations of speculation, you risk being labeled as fringe, as sensationalist, as the guy who didn't follow the playbook, but that discomfort shouldn't prevent us from following the data wherever it leads. That's the opposite of science. That's confirmation bias. Loeb has been vocal about this. He's argued repeatedly that the stigma around discussing non-natural origins for unusual objects is itself unscientific. Science is supposed to be agnostic about outcomes. You propose hypotheses, you test them against evidence, you follow the results. If an artificial origin hypothesis can be tested and falsified, then it's a valid scientific hypothesis regardless of how uncomfortable it makes people, regardless of how it sounds. That's what science is. The challenge is figuring out what observations would actually distinguish between natural and artificial origins. What would we expect to see differently? What measurements, what patterns, what signatures would be diagnostic? What would be the test? For a natural comet, we'd expect activity to correlate directly with solar heating, simple cause and effect, close to the sun, more heat, more activity, far from the sun, less heat, less activity. We'd expect the composition to fall within known ranges for ices and rocks formed in protoplanetary disks. We'd expect structural variations to be random, reflecting chaotic accretion processes where particles just bump into each other and stick. We'd expect the trajectory to show small perturbations from outgassing that match the direction and intensity of observable jets. The comet jets out material that creates a tiny rocket effect that slightly changes the trajectory. We can calculate what we'd see. For something designed, something artificial, we might expect precise threshold behaviors, activity that switches on or off at specific conditions rather than gradually changing. We might expect unusual symmetries in the structure or composition, perfect geometry. We might expect trajectory corrections that can't be explained by passive outgassing. We might expect radio emissions at frequencies that suggest modulation rather than natural plasma processes. We might expect patterns, order, design. Have we looked for those things? Have we conducted the tests that would allow us to distinguish between these possibilities? That's what Loeb is asking NASA to provide data for. Let the scientific community examine everything. Let independent researchers look for patterns. Let the analysis be as comprehensive as possible. Because here's the reality. We are living in a moment of cosmic significance. For the first time in human history, we have the technology to detect, track, and analyze objects from other stellar systems. We can point our most advanced telescopes at these visitors and gather data that would have been impossible even 20 years ago. The James Webb Space Telescope, launched just a few years ago, is giving us insights into the composition and structure of objects at unprecedented resolution. Our network of space-based observatories provides continuous monitoring that ground telescopes alone could never achieve. This is the golden age of interstellar object research. but it's also a brief window. These objects pass through quickly. Threeey Atlas will be gone within months, disappearing back into the vast emptiness between stars, and we may never see another interstellar visitor for years or decades. Each one is precious. Each one is an opportunity we can't afford to waste. The window closes fast, and that's why the explosive brightening matters. That's why the missing dust tail matters. That's why the radiation crust matters. That's why every anomaly, every unexpected behavior, every deviation from our models deserves serious attention, because we're not just studying a comet, we're gathering data that could reshape our understanding of what exists in interstellar space, what's out there. What's drifting between the stars right now? Think about the implications if interstellar space is filled with objects like Threeey Atlas, billions upon billions of them, drifting between the stars, carrying within them the chemical signatures of distant stellar systems, possibly even carrying the building blocks of planets yet to form. The galaxy becomes a vast ocean of potential, raw material constantly in motion, constantly redistributing itself across light years, constantly flowing through the cosmic void. That's a fundamental shift in how we understand the universe. That's meaningful. But think about the implications if even a small fraction of those objects is something else. If among the countless natural comets and asteroids wandering through the darkness, there are also artifacts, probes, constructs sent out by civilizations that existed millions or billions of years ago, what would that mean for our understanding of intelligence in the universe? What would it mean for our place in the cosmic story? That's not a small question. We've searched for radio signals from the stars. We've looked for laser pulses, for engineered structures around distant suns, for any sign that we're not alone in this vast universe. We've been looking outward, looking at the stars, trying to detect some signal, some beacon telling us that intelligence exists somewhere out there, but maybe we've been looking in the wrong place. Maybe the evidence isn't out there among the stars. Maybe it's here, passing through our own solar system, disguised as natural objects, because that's exactly what they'd be made of. Interstellar probes wouldn't look like spaceships from science fiction. They wouldn't have flashing lights and sleek designs. They'd look like rocks, like ice, like comets. They'd blend in, they'd hide in plain sight, and the only way we'd know the difference is through careful, detailed analysis of their behavior and composition. Which brings us back to the data, which brings us back to transparency, which brings us back to the fundamental question of whether we're being as thorough as we should be in investigating these objects. The next few weeks will tell us a lot as Threeey Atlas moves away from the sun. As we continue to monitor its brightness, its spectrum, its trajectory, we'll gather more pieces of the puzzle. Maybe those pieces will fit together into a clear picture of an unusual but entirely natural comet. Beautiful, interesting, just a comet we didn't expect to exist. Maybe the pieces will reveal patterns that challenge our current understanding and force us to expand our theories, push us to think differently. Maybe, and this is the question mark that hangs over everything, maybe they'll show us something we weren't expecting, something that makes us question our assumptions about what's possible, about what exists out there in the darkness, about whether we're as alone as we've always believed. One thing is certain, we're watching right now at this moment. Telescopes around the world and in space are pointed at Threeey Atlas. Scientists are analyzing spectra, calculating trajectories, modeling internal structures. Amateur astronomers are sharing observations, comparing notes, contributing to a global effort to understand this visitor. The data is accumulating, the picture is becoming clearer, and whatever we discover, whatever the answer turns out to be, it will change something about how we see the universe, because every interstellar object teaches us something new. Every visitor from the darkness brings with it information we couldn't obtain any other way. Every anomaly is an opportunity to refine our theories, to test our assumptions, to push the boundaries of what we know. Threeey Atlas came from somewhere. It traveled for billions of years to reach us. It survived conditions we can barely imagine, and now, for a brief moment in cosmic time, it's here. Close enough for us to study, close enough for us to learn from. It's performing in ways we didn't predict, behaving in ways that challenge our models, revealing properties that force us to think harder about what interstellar objects really are, what exists in the space between stars, what the universe has to tell us. The question isn't whether Threeey Atlas is strange. It clearly is. The question is what that strangeness means. Is it the strangeness of a natural universe more diverse and complex than we've given it credit for? Or is it the strangeness of something else? else, something that makes us reconsider fundamental assumptions about our place in the galaxy, about what we should be looking for, about what we should be prepared to find. Time will tell, the data will tell, and that's why we need all of it. That's why transparency matters. That's why transparency will always matter, regardless of what the final answer turns out to be, because in the end, this isn't just about one object passing through our solar system. It's about how we approach the unknown. It's about whether we're brave enough to follow the evidence wherever it leads, even if it takes us to uncomfortable places, even if it challenges what we thought we knew. It's about whether we're willing to ask difficult questions and accept uncertain answers, whether we can sit with not knowing, whether we can remain open to possibilities while remaining rigorous in our analysis. Threeey Atlas is still out there, moving away from us at over 100,000 miles per hour, carrying its secrets back into the darkness. But for now, for these precious weeks, while it's still visible, we have a chance to learn, to observe, to question, to wonder, and maybe, just maybe, to discover something that changes everything. The interstellar visitor has arrived, it has performed its unexpected display, and it is now departing. What it leaves behind is questions, important questions, questions that deserve answers. The universe is speaking to us through these objects. Threeey Atlas is speaking. The question is whether we're listening carefully enough to hear what it's saying. Are we? 1.